And we get to the fun part, intractability. Well, actually, coming up with algorithms and this part are fun, right? But this is really, really cool. We have covered algorithm design patterns, right? Kind of solutions. Greedy, divide and conquer, dynamic programming, and then we have talked about duality, which we did for chapter 7 with flow and cut. Then we're going to talk about reductions a lot for showing NP completeness. Reduction is just transforming a problem onto another, and then if you know how to solve the other one, then life is good, you just solve it, right? You need to be able to transform the problem, solve the other problem, and then transform the solution back into a solution for your problem, right? But that means, oh, now I know how to solve. Now we are going to see it's not true, but kind of an anti-pattern for algorithms, which is NP completeness. We are going to show a class of problems that are hard to do. An NP-complete problem is actually, it's kind of the lowest level of hardness that we know. And basically what we assume is that, well, the cool thing about this is that we don't know much about them. We know a lot about NP-complete problems, but we don't know the most important thing is, can we solve them in polynomial time? We don't know, we believe we can't, or most everybody believes we can't, but it hasn't been proven. So the thing about NP-complete problems is that if you solve one, you solve all of them. We have proven that you can go from one to the other. So we have this whole class of problems that you can go from one to another. So if we solve one, we'll be able to solve all of them in polynomial time, which is why we believe that, no, we can't solve them in polynomial time. Then you have word stuff, which is p-space, which we don't really have. They are way harder than NP-complete. And then we have undecidability, which is the ultimate in coolness. We have problems that we can describe that we know we cannot solve in general, which is really cool. You get to see this in theory of computation. You'll have to take that one, right? That one should break your brain even more. So on that one, you get to formally specify what's a computer with different models of what's a computer and infinite memory and stuff like that. And then formally prove that there are things you cannot compute and there are things that are NP-complete and all of that stuff. Here we do it more informally at a higher level. So it's a slightly different viewpoint. And this chapter we are going to talk mostly about NP-complete. The idea is to try to classify our problems, right? And see whether we are doomed or not. The pseudo question is, which problems are practical? Which problems can we solve in practice? The pseudo answer is, well, if you have a polynomial time algorithm. Is that a good answer? Sorry? The one we got, but is that a good answer? What are problems with that answer? What problems do you see with that answer? Is n squared the same as 1 million n squared the same as n to the 25?
Depends on n.
But right, normally no, right? I mean that. So the constants may be hard. The exponent may be hard. Something that's n squared, n cubed, maybe n fourth is doable, and above that, we're doing it, right? So there is, and that will vary also on the size of that. So it's not quite perfect, but a cool thing is the definition is relatively broad and robust, and it tends to be reasonably with practice because we normally don't do algorithms for n to the 25th. So it's kind of a virtuous type circle, right? And there is actually a ton of practical ways of solving these other problems that we cannot solve in practice, right? And that's basically you say, well, I don't necessarily need an optimal thing, I just need a good enough thing. And then there is a ton, and we'll cover some of that ton of good enough solutions. But for these kinds of problems, we have polynomial time algorithms, right? Shortest path, and we have really cool polynomial time algorithms. Min cut, we have pseudo polynomial time algorithms, right? Vertex matching, most of these, we have polynomial time algorithms, even for something like primality testing, where you're going to test where a number is prime. Well, I just go through every number up to that one, right? And check. It may take a long while, but it's polynomial. There is a bunch of them on this side, where we will see they are NP complete. So chances are that we cannot find a good solution. They are decidable. We could find a solution, but chances are that the only optimal thing is to try every possible combination. And there is a ton of them. So what we want to do is try to classify problems according to those that can be solved in polynomial time and those that cannot. We have some that we can prove that they can, but then we have this huge class of well-known, well-studied problems where we don't quite know, which are the NP-complete problems. This is probably the coolest idea ever. It appears in a bunch of places, but here's the idea. Suppose we know we can solve a problem y in polynomial time. What else can we solve in polynomial time? Well, we can come up with a reduction, right? And in this case, we are doing polynomial time reduction. You do the same for undecidability and decidability. So a problem x reduces to problem y, or polynomial time reduces to problem y, if for an arbitrary instance of problem x, I can solve it by a polynomial number of standard computation plus a polynomial number of calls to some oracle that solves the problem y, to the function that solves the problem y, right? So if this function is polynomial and these two are also polynomial in time, then the end result is going to be polynomial. Does that make sense? Yes. In programming terms, what we are going to do is have a solve x, right? And what we're gonna, if we can do in pseudo Java-ish code, um, something like this, right? Where we are going to call a reduction procedure, we are going to solve the other problem y, then we are going to transform back our solution. And if we know, right, that all three of those function calls take polynomial time, then we are okay. The total is going to be polynomial time because it's just the sum of those three things. Does this idea make sense? Yes? Cool. So now we can go do tons of examples of this thing, right? The notation that we're going to use is less than or equal with a p. So it's less than or equal in polynomial time, right? It's not less than or equal, it's reduces to or something like that. So, of course, the instances of y must also be of a polynomial size, and the number of calls needs to be polynomial size. So we could end up calling solve of y to, we may need to solve 3 different problems of y or something like that. And of course, x less than or equal p of y is kind of the reverse of y less than or equal p of x, right? So x reduces to y is not quite the reverse because we have the equality of y reduces to x. We can use reductions for 3 main purposes. If I can find a reduction and I already know how to solve y, then I already know how to solve x in polynomial time. I can also do it to establish intractability. If I say that x reduces in polynomial time to y, and in this case it's the other way around, I know that x cannot be solved in polynomial time, then I know that y cannot be solved in polynomial time. Why?
Because x is less than or equal to polynomially to y. So if you can't do x, meaning like the runtime of x is enormous, then the y could be enormous plus 1 plus 2.
Yes, because if y wasn't enormous, right, I could reduce x to y, solve y, and come back, right? And so given that I have proven that I cannot do that with x, then it follows that I cannot do it with y either. I can also use it to establish equivalent. If x less than or equal, if x reduces polynomially to y, and y reduces polynomially to x, and we could use the notation x 3 var, right, which is equalish polynomially to y, and that basically tells me that they both have the same-ish runtime, right? They are either both polynomial or both general. In a way, right, the reductions allow me to classify problems according to relative difficulty. This is harder than this. So now let's go do problems and see how we can go from one to the other. And most of these problems are actually NP complete, so there is no good algorithm for this, right? So one problem is the independent set. Given a graph G of vertices and edges, vertices V, edges E, an integer K, is there a subset of vertices S a subset of B such that the size of S is greater than or equal to K, and for each edges, at most one of its endpoints is in S. At most one, so that means they are not directly connected to each other, right? So is there an independent set in this graph of size 6? Well, yes, there is, right? They helpfully drew them for us. The 6 black guys are an independent set of size 6. Is there one of size 7? Maybe. What's an easy way of solving this problem if you have unlimited time? What could you do?
Find the edges that have the least, find the nodes that have the least edges.
Finding nodes that have the least edges, that would be a heuristic, right? And what do you do with that?
Alpha beta prime.
Sorry?
Alpha beta prime.
You could do, right? But what are you trying to do, right? What's the solution that's guaranteed? What's the solution that you use for programming interviews? What do you do? Sorry?
Breadth first search, or would you search through the graph, or is it too big?
You're not searching through the graph, right? You're searching through what? What's your solution? What does your solution look like? Or, yeah, right? It's a set of vertices, right? So what can you do to find a solution? Right? Every possible subset of vertices, right? Just brute force it, right? How long does it take to brute force it? How big is the set of all the possible subsets?
It'd be S to the. It'd be exponential.
Yes, right? Why? How can you generate all the subsets? Well, I get one bit for each one of the elements, and I do 0 or 1 for included or not included in the set, right? So that's 2 to the n. Does that make sense? Does that suck? Yes. But, hey, I can solve it. It's not that bad. I can solve it. It's just going to take me forever, right? Can I solve it with a polynomial algorithm? We don't quite know, but we believe no. Now what we are going to do is show another problem and then show that that problem reduces to this one, right? So we are going to show that the vertex cover problem is equivalent to the independent set problem, right? That means vertex cover reduces to the independent set, and independent set reduces to vertex cover. What is the vertex cover problem? Sorry. Independent set. Vertex cover is given a graph G, integer K, is there a subset of vertices which size of S less than K, and for each edge, at least one of its endpoints is in X. I'm trying to do the reverse. I'm trying to get a set of vertices so that everybody goes here or comes from here. That's called a cover. And it is basically the other set, right? So what we are going to show to show that they reduce to each other is show that S is an independent set of size k if and only if V minus S, so the other edges, is a vertex cover of size n minus k. So if you have an independent set, the complement of the vertices will be a vertex cover. And so going from one to the other is just, right, complement of two sets. So let's show that, let's assume that S is an independent set of size k. What does being an independent set means? There are no vertices from a vertex in S to a vertex in V minus S. Sorry, there's no, let's go look. Independent set, for each edge, at most one of the endpoints is in S. So there is no vertex from a vertex, there's no edge from vertex in S to another vertex in S. That's an independent set, right? What does that mean, right? That every edge has at least one endpoint, maybe both, in V minus S. But it cannot have both of them in S. Right? So it is a vertex cover. So V minus S is of size n minus k. Consider an arbitrary edge, UV, given that S is an independent set, either U is not in S or V is not in S, right? So either U is going to be in V minus S or V is going to be in V minus S, or both. And so V minus S covers the graph, right? Covers the edge, and so it covers the graph. Now, going back, if V minus S is a vertex cover of size n minus k, then given two nodes, U and V, any two nodes U and V in S, the vertex UV, the edge UV cannot be in the set of edges, since that would mean that V minus S is a vertex cover. So no two nodes in S are joined by an edge, and so S is an independent set. In a way, this is more duality again, right? We have proven that these two things are dual of each other. If you solve one, you solve the other. Now let's do one slightly more complicated. Set cover. Given a set U of elements and a collection S of subsets of U, no, just a given set of subsets of U, and an integer k, can you find a number of subsets less than or equal to k such that their union is equal to U? One example would be, right, one possible application would be, given that there is n pieces of software with different capabilities, what's the smallest number of programs that you need to buy to get that capability, right? To get the whole set of capabilities that you need, right? How can we solve this by brute force? What's brute forcing in this case?
Every single subset.
Every single combination of subsets, right? So try every subset of the set of subsets that you were given. Does that make sense? We are going to show that vertex cover reduces to set cover. So how do we prove that? We get a vertex cover instance, show a polynomial transformation to the set cover problem, and a polynomial transformation from the solution back to the solution of the vertex cover problem, right? So what can we do? We are going to build weird stuff, right? Our universe is going to be the set of edges. Our universe on the set cover problem. It's going to be a set of edges. And now we are going to have, for each node V, we are going to have the set of all the edges that match to it. And that's going to be the subset. So how many subsets am I going to have?
The amount of nodes.
The amount of nodes, right? If I solve it, right? The lemma says the graph contains a vertex cover of size k if and only if this set cover instance USK contains a set cover of size k. How are we going to construct the solution, right? Given x be a vertex cover of size k in G, we are going to show that the solution, that would also be a solution for the set cover. And going back, we are proving both sides, right? If we have a set cover, then the corresponding set of vertices in X is also going to be a vertex cover. Isn't that cool? What's a vertex cover? A set of vertices such that every edge has at least one endpoint there, right? So since we did the subsets by all the edges that match there, if the union of that is all the edges, then that will be a vertex cover, right? And vice versa. Isn't this cool? We can go from one to the other. They are the same-ish problem. They can be reduced, right, to each other. And given that the reduction is polynomial and all of our sizes are polynomial, we're good. If we could solve one, then we can solve the other. Isn't that cool? Isn't this confusing? Yeah, it's good. Now we are going to confuse you even more. These are, let me do a meta thing. Why are we confusing you guys? Computer science is all about abstractions, right? What we are trying to do with all this stuff is to, first of all, to show you a bunch of well-known problems to add to your repertoire. But also, we are practicing how to be more and more abstract, right? In this case, we are talking now about classes of problems and sets of subsets and things like that. So you go 1 or 25 levels up in the abstraction. One well-known problem in theory of comp and algorithms and that stuff is Boolean satisfiability. We define a Boolean formula as being composed of literal, which is either a Boolean variable or its negation, and clauses, and there's slightly different ways of defining this thing. The one that we are going to use is we're going to say a clause is a disjunction of literal. What does disjunction mean?
Ands and ors.
Almost. What's a disjunction? Ors only. Conjunctions is only ands. Disjunction is only ors. So here we're defining a clause as only disjunction, only ors. And then a proposition is going to be a conjunction of disjunctions. So it's a propositional formula that's a conjunction of clauses. You could do it the other way. Why are we defining it as conjunction of disjunctions instead of letting you mix and match? So you don't have parentheses, right? We could have done it the other way. A disjunction of conjunctions, right? But either way, you don't need parentheses. And so we get kind of a linear structure as opposed to a tree. Satisfiability is given a conjunctive normal form formula, do you have a satisfying truth assignment? So can you give truth values, true or false, to the xi so that the formula is true? And tree SAT is a SAT problem where each clause contains exactly 3 literals. Now we are making it even more reductive in a way. All your clauses have 3, so the only thing that you can vary is the size of the conjunctions, right? How many conjunctions are you going to have? How many clauses are you going to have? But each clause is the exact same size. What do we use this for? To torture graduate students. But it's also in many different forms used for electronic design. Logic, electronic design, computer architecture, that kind of stuff. And what we are going to show is that tree satisfiability can be reduced to an independent set. So tree SAT reduces polynomially to an independent set. What does that mean? Well, given an instance of tree SAT, we can construct an instance of independent set, and then translate the solution back, right? We are gonna, now we're going from conjunctions to graphs, right? So we are gonna construct a graph, and each graph, this graph is going to contain 3 nodes per clause, 1 per literal in the clause, right? They are joined together in a triangle, and then we will also connect all the literals and their negations together. So all the nodes that correspond to the same literal or negation together. What does an independent set mean, again?
A set so that each node occurs within itself once? Or
Each, there are no edges that connect it to each other, right? There is no edges that connect 2 nodes in the set.
how does that work with sets as opposed to graphs?
I mean, an independent set is a set of nodes in a graph,
Okay.
such that there is no edge between 2 nodes in the set. right? And so what's going to happen is that we are joining each one of the clauses, right? So we require at least one of them, and then we are joining the nodes that correspond to the same literal. So if we find an independent set, right, that is a set that there's no edges between the elements in this set, that's going to give us a satisfaction of the problem. So our lemma is going to be G contains an independent set of size k equals size of phi, if and only if phi is satisfiable. So if we have an independent set of size k, right, S contains exactly one node in each triangle, right? And we can set these literals or the right to true or false, right? And that will satisfy all the things. Why, right? We are joining, in this case, we are joining not x1 with s1, right? So either we are going to have x1 or we are going to have not x1, but not both. Because if we have both, then they are not an independent set, right? So that means that we are only going to be turning on either x1 or not x1, and the same for x2 and the same for x3, and however many variables we have. Does that make sense? No? Let's see. Let's solve the problem, right? Let's find for this graph an independent set, right? Okay.
Specifically of size 3, with k equals 3.
Yes.
Which I guess you can also. It's a conjunction. So, man, there couldn't be a better word. It
So what would be an independent set here? We'd have x3, right?
We have the other x3 as well in the second clause.
Well, it's a set, so
Yeah, but it's two different nodes.
do two different nodes of the same value count as two different nodes?
Let's see. What was our size in here?
It's x1, x2. It's
Oh, the size is the number of clauses. Sorry.
yeah. And it says that the instance is x1, x2, and x4.
So in this case, right, we need 4. Well, in this case, we have 3 clauses. They changed things in the middle. So we have 3 clauses, so we need 3 sets. right? So we are choosing x3. We need to choose. So I'm done here. I'm done here, right?
We're picking 3 separate nodes in our graph.
Yes.
Okay, so technically the x3 in the first little triangle and the x3 in the second triangle are different nodes. So you
Yes.
both of them, right?
Yes.
And we need x4 from the last clause there.
And that satisfies it. And it's easy from thinking of it this way, but in terms of the algorithm, I think I'm still lost.
What do you mean the algorithm?
Or just never mind. I'm still wrapping my head around it.
So, and that's enough, right? That's all I really need, right? I can't use x2. I can't use x1.
X1 is
Yeah.
Can I use
You can do
not
like-
x1?
Yeah, X
You do
just
that.
go next to X.
I mean, I would need not x1.
Right. As your first one, then you can still do x3 from the second one, x4 from the second.
Yeah. Yeah. So there's gonna be more than one.
So we can have a bunch of different independent sets that work depending on the problem.
Yes.
Okay.
Yes. Because in a way, here my independent sets are a small size,
Yeah.
right? Relatively to the problem. So I'm gonna have, if I have satisfiability, chances are that I have a ton of ways, depending on the problem.
I get the problem is just building off of this, continuing on.
Yeah.
The reduction.
So, given an independent set, right? Any independent set, you can only have one variable on each triangle, and given that each literal is joined to its negation, if it appears, right? Then you will never have both of them together. Right? So that is a consistent truth assignment, right? Because at least one of them will be true in each triangle, which is in each clause, so the conjunction gets satisfied. And we cannot have a contradiction, because those would be the extra edges, right? And conversely, given a satisfying assignment, right, then you just need to select one of them, right, from each triangle. And you know that that will be a cover, right? A independent set, sorry. Isn't this cool? We can go from one very abstract thing to another very abstract thing. The only problem with this, and I struggle with it myself, and I struggle to the nth power when trying to read your thoughts, is that it's very easy to nod and BS yourself into thinking that you understand.
Well, I'm nodding, but I don't understand.
So yeah, it makes sense, but for the vast majority of people, it is almost impossible to memorize these things because we're going to see 20, right? So you need to understand the techniques and kind of come up with them, as opposed to try to memorize. Especially if you memorize without understanding, you end up with something that doesn't make it.
So the basic idea of this is taking large problems that can't really be broken down into subsets. So just large, difficult problems that you can't really handle, and likening it to another kind of problem that might be related. And if you can solve that other related problem, you can solve the difficult problem.
And what we are going to show is that there is a ton of problems that are related to each other, that they are equally difficult, and we don't really know whether there is a polynomial time algorithm. We have been searching for one for 50 years, so chances are there isn't one. But we haven't been able to prove it. That's the set of NP-complete problems. Some of the reduction strategies that we have seen, simple equivalence, right? Independent set and vertex cover, they're basically the same thing, right? A special case to a general case, the vertex cover is kind of a special case of the set cover. And then coming up with gadgets, right? This stuff that transform one into the other, they call them gadgets. We also have transitivity. If x reduces to y and y reduces to z, then x is going to reduce to z, which is cool. Right? Now, a little bit of terminology. We have two different kinds of problems. Let me, we have actually three different versions of the same-ish problem. The decision problem, right, is given an instance of a problem and an integer k. Is there a solution of size k or less, right? So for the vertex cover is there a vertex cover of size less than or equal to k? The search problem says find one, right? And they're not quite the same, right? If I have a reduction, I can solve the decision problem without necessarily being able to come back and transform the solution, know that it exists. I don't know what it is, but I don't terribly care. You just ask me whether it was true or false, whether one existed. For the search problem, we need to be able to come back, right? The decision problem, the cool thing is that they are the same. They are, or if one is polynomial, then the other one is also polynomial, right? So how can I, given a decision problem, how can I convert it into a a search problem, right? Well, given that I know that I have a decision algorithm, right? I will just determine if, take a vertex, right, out and check whether I can find a vertex cover of size k minus 1. And if I can, then that thing is in the vertex cover. If not, then it's not, right? And so I can do n things, right? N instances of search, right? To find n instances of decisions, to find a solution to search. But it's still a polynomial, right? I need to do n decisions, but, right? It's still polynomial, so, and of course, if I can find it, right? If I have one that can find it, then I'll just run it with all the values of k, right? The optimization problem is, rather than given size, find the one with the smallest size. And given that I have kind of a max size, right, then I could do linear, but I probably rather do binary search, right, over all the possible k's to find the minimum size, right? So I try, can you find one with this k, then half, and half, and I can run the search, which can run a bunch of decision ones, but it's still a polynomial number, right?
Don't you have to sort it though? Which is, I guess, polynomial. You gotta sort your k's by.
My k's are sorted because k is just a number. K is just an integer.
Okay.
Right? So I'm just searching over k.
What is k star exactly there? Is that
The correspondent, the corresponding thing.
the size,
Yeah.
I guess that's what I was saying would have to be sorted, I guess is what I meant.
But they're just integers, right?
Yeah, so I guess
And so find and optimization problems are polynomially solvable. If you can find one, you can solve the other ones. So the optimization problem is the hardest one, but if you have a decision one, then you are okay. Does that make sense? No? Sorry? You wrote it down, but it doesn't make sense?
That's all I do in this class is write things down. I'm going to go to YouTube later.
And read the book. The book is
Yeah,
actually good. Yes. But you need to work this out by yourself, right? Because it's very, very easy to just nod and not understand. Here is another interesting one. Hamilton, besides singing really cool hip hop, is a different Hamilton. Hamiltonian cycles, right? Is there a cycle that contains every node in V? So given an undirected graph, is there a cycle, simple cycle, so you cannot repeat edges, that contains every node? When you see something like this, well, it is, and they just show me the cycle. When you see something like this, right? What could you do?
brute force
How would you brute force it?
every single cycle.
Every single subset of edges and see whether it's a cycle, right? Whether it's a Hamiltonian cycle, right? Now, this is actually relatively easy to understand. Given a digraph, now directed graph, is there a simple directed cycle that contains every node in there? And what we can do is cheat and convert every node into 3 nodes now, and convert every edge into an undirected edge, right? And for every node now I have in the node and out, and then I will convert the edges that were coming in into undirected edges to be in, and then the ones that were coming out into undirected edges to or from the out one. So I end up with 3 times the nodes, right? Because now for every node I have the real one, the in and the out. And I connect each in to out, so it's actually not 3 times. It's about the same number of edges, right? Slightly more. So if I have a directed Hamiltonian cycle, say that D had, well, actually, this thing doesn't have a cycle at all. Imagine that I make an edge from D to A and then to B to C to E. No.
Maybe the next page.
From
this,
E to D and then from A to B, from D to A. So I can do just this. Ha! So I need to add edges from E to D, and then from D to A to B, and B to C, and cheat horribly, right? But give me a Hamiltonian cycle. I will have one in here too, right? Because I can navigate this one. And then it doesn't terribly matter which way I'm going, but I would also have a cycle in here, which would be a horrible thing to show. Coming back is even easier. I either have black, white, blue, right? Or black, blue, white, right? In my cycle. And so I can just merge those edges. It's either the cycle or its reverse. And then let me tell you that 3-sat reduces to the directed Hamiltonian cycle, and then keep the construction because it is horrible. Actually, well, yeah. Actually, no, there is one that's even more horrible. Okay, we'll talk about this one next class. And give you back 5 minutes of your life. And hopefully 1 or 2 neurons that still survived.
yeah.